and we'll start from current slide. All right, here we go. Wanted to know if there are any questions for anything we've done so far. Okay. All right, this was Wallace's formula. I think we went over that last time. I believe we probably beat it to death. So any questions on that? That's where my slide said it was starting, but was started at the top of the next page. Okay. Integrals involving powers of secant and tangent. Is that where y'all have that we were, or did you have something else?
I had on example 4.
Example 4. Yeah, we haven't gotten there yet. Yeah. Yeah. So this is leading up to example 4. Okay? Now, remember, flashback here, when you have integrals of sines and cosines at various powers and stuff, the main thing you first look for is either one of those exponents odd. If they are, it's sort of a piece of cake. I mean, yeah, there's some things to do, you got to do. The second, if neither one of them are odd and both of them are even, then you use the half angle formula. It's a double angle formula for cosine. Basically, it's the power reducing formula that for cosine squared. So you go that route. Now we're dealing with secants and tangents. And y'all already reminded me, remember, of what some of the characteristics we're going to focus on. And what were they? Do you remember? So you have your Pythagorean identities that deal with even powers, always squares, of secant or tangent. Okay, and there's Daniel. Okay. And the other is the fact that the derivative of tangent is, tell me.
1 minus secant squared.
Okay, you're giving me the Pythagorean identity. Tangent squared is secant squared minus 1. Okay, that's Pythagorean identity. And secant squared is 1 plus tangent squared. Yeah. Okay? But what about the derivative of tangent? Help me, somebody. I'm drowning. It's secant squared. Derivative of of secant is rather strange. Secant times tangent. Okay. All right. So with those in mind, let's hit this. Guidelines for evaluating integrals involving powers of secant and tangent. When the power of secant is even, that m is even, and positive, needs to be positive, save a secant squared factor out, okay, because that is derivative of tangent, right? Okay, so we save that out for that one. And then the rest of them are still even because the secant's even, and then use the Pythagorean identity to get this remaining secant, even secant powers into tangent, even tangent powers, okay? So convert those remaining factors to tangents. Then you expand and integrate, whatever it takes, okay? So, point here, this m is some even number. We'll call it now 2k. Okay, 2 times k, because even number, k can be anything. Tangent doesn't matter what it is. Okay, it can be even, odd, fraction, decimal. Sorry. Sorry. Y'all awake yet? Okay, good. Okay. Goodness gracious. Sneezes. Okay. Now, we'll take 2 of these away, okay, and move them down with the dx. So secant squared there. So that leaves us a secant to the 2k minus 2, because we subtracted 1 off of it, or you could call that a secant squared to the k minus 1. Okay. K being some number. It doesn't have to be even or odd. It doesn't matter. Tangent we leave alone, and secant squared we have down there because that is the derivative of tangent squared. All right. Now, since the secant squared is 1 plus tangent squared, right? That's to the k minus 1 power. Then you have your tangent x, tangent to the nth, and secant squared, okay? Which is our derivative of tangent. So now we have everything in terms of tangents and the derivative of tangent. All right. And from there, you go to town, okay? You first raise this to whatever power that is. That could be a little hairy, but not too bad. And then multiply that by whatever power that is. And then you have a polynomial in tangents, and every one of them has a tangent in it. And that's the derivative of tangent. So you can do your substitution and get that done. Okay. Next, when the power of the tangent is odd, okay, power of tangent is odd and positive, save a secant tangent factor, because that's the derivative of secant, and convert the remaining factors to secants. Hey, got it done. Okay? It will work whether secant is even power, it works. When tangent is odd power, it works. Now, what if secant's odd and tangent's even? Well, we'll worry about that tomorrow, okay, or later. Okay. So, what we do here, remember the tan is odd, so we're going to take one secant and one tangent out for it because that's the derivative of the secant. Okay, and that's going to leave us a secant m minus 1 and a tangent of 2k, which is tangent squared raised to kth power. Well, this is the derivative of secant. This is all in secants. This is secant squared minus 1 to the kth power. Expand that, then multiply this by each term, and that is your derivative. So that's pretty straightforward too. All right. Now, when there are no secant factors and the power of tangent is even and positive, ooh, boo hiss. No secants there to mess with, and the tangent is even and positive, convert a tangent squared factor to a secant squared factor, and then expand. So this is tangent, and it's even. If that was odd, no sweat, but it's not. It's even. Okay? So take a tangent squared out, that's the derivative of secant. Okay? No, I'm sorry. It is a derivative of secant, but they say convert. Yeah. Back off a moment here. This, I think, is the one that you want to convert to secants. I don't see how that helps you. The derivative of secant is tangent squared. So you take this, which is still even, right? Because it started out being even, you pulled this out, and this is some even power. Convert that to secants. I think they have this in the wrong thing. And then you have this to some power, whatever power that is, and okay. Please tell me the book has this right. No? We'll see when we start doing examples, but yeah, something looks wrong here. Now this one, when the integral is of the form secant mx, where m is odd and positive, that didn't fit anything that we had before. No, I'm sorry. They're right. Derivative of tangent is secant squared. I was doing it backwards. Yeah? Yeah. Sorry about that. So that statement is true there, but how does that help you do anything? Tangent times secant, that can be, you can probably get a derivative of a secant out of that, okay? And then you have tangent to an even power, and then you can, yeah, that would be. What you do from that point on is a recursive thing. They don't explain it here, but we'll get to it later. So let's move to this one. Secant to the mth x, where m is odd and positive, boo hiss, we use integration by parts. Ha! You remember that, don't you? One part will be a secant to the double thing. That would be the thing you integrate, because that's going to be derivative of you break it into one secant and the other powers of secant that will be even, because m is odd. So we'll do this. An integration of our parts, you'll see when we do the examples. So let's do that. Hard to talk about them without having some numbers out there. And then number 5, when the first 4 guidelines do not apply, try converting to everything to sines and cosines. That may not be a bad idea anyway, okay? It may help some of these others that are a little more sketchy. So we'll check and see. Okay, let's move to example 4. That's where you wanted to start, right? All right. How would you approach that problem right there? Say that again? A little louder. Yeah, there's a radical on the bottom. We don't like that, do we? What can we do with it?
Rewrite it, please.
Yeah, rewrite it. Whoa, let me get my pen set up. Okay, how would you rewrite it? The integral of? Tangent cubed x secant to the negative 1/2 x dx. All right. Without a doubt, we need things in terms of secants, because you can't do much else with that to the negative 1/2. And this is a tangent cubed, so what's the derivative of secant? Secant tangent, okay? Is that the way to go with this? Yeah, I believe that'll work. Okay? This is going to take some sort of creative thinking here, but it will work, and we can do that, all right? All right, we want to pull out a secant and a tangent, because that's derivative of secant, and we're going to be integrating secant, so we need a d-secant in there. So this will be the integral. We're going to pull out a secant, secant x tangent x dx, because that's the derivative of the secant, right? So this will leave us a tangent squared x, right? And this will be, since we pulled out a secant x, that's a secant to the 2/2, this is left being a secant to the minus 3/2 x. Okay? Now, if you don't believe me there, go back and multiply through. Tangent squared times tangent is tangent cubed. That works. Secant to the minus 3/2 times secant, which is to the plus 2/2, that would be secant to the minus 1/2, so that does work. So that is the correct, you might say, division, or you could call it factorization. Okay? Now, secant tangent, secant x tangent x dx, remember, is the derivative of secant x, right? That you need to keep in mind, right? All right. Now, with that done, we need this in terms of secant x2. Well, what is tangent squared in terms of secant?
1 minus secant squared x.
Okay. The other way.
Oh, 1 plus.
No. Secant squared x minus 1.
Why does that make a difference?
Second?
Why does that make a difference?
Because it's the negative of the other one that you said. So if you had said a negative in front, that would have been okay.
Oh,
Right. Okay? Right?
yes, sir.
Okay. This is multiplied by secant to the negative 3/2 x, and then I'm just going to go and write this as d of secant x. Okay. Now, you can do that, or if that isn't something you like to do, if that's not comfortable for you, we can now do our, let's do it. I can tell it's not comfortable. Okay, is it? All right.
I put it down the other way.
Oh, you did, okay. All right, we will write that as secant x, I'm going to keep the parentheses there, tangent x dx. Okay. You don't have to have the parentheses there, but just to sort of separate. Well, what I'll do is this. And maybe lose those parentheses. That may make it better. Y'all okay with that?
It would have been d of secant x dx. I think we would have written that.
No. Derivative of secant x is secant x tangent x dx. If you're doing differential. Okay, and that's what I was trying to do. So we'll do it. All right. Next step, let's multiply these two together. And what would that give you? Secant squared times secant to the minus 3/2 is?
It'd be secant to the half.
1/2 x minus secant to the
Negative 3.
minus 3/2 x. I'll put those in parentheses and then do secant x tangent x dx. Sometimes I get the writing too fast and I write tangent x as tax and secant x we won't even go into what I call that. Okay, never mind. Okay, I'll try not to write too fast. Okay. All right, enough of that. Now, we've got everything in terms of secant x, so guess what our u will be if we're going to do a substitution? That's what you want to do? Okay, what will be u?
Secant x.
Yes, let u be secant x. I can't write now. Secant x. I did it again. Yuck. Write too slowly and talk too fast. Okay, secant x. Then, what's our next step? Du is equal to secant x tangent x dx. See, that's why I did it that way. Okay. Now, let's plug in what we've got then. Yuck. Okay. This will be the integral of, if u is secant x, what's secant to the 1/2 x? U to the 1/2 minus u to the minus 3/2 times du. Nice, huh? I think we can do that, can't we? Whoops. Okay. And by the way, I should have said this earlier. I was going to wait till more people came in, but they don't seem to be coming immediately. Again, I think I mentioned to you last time, Mr. Rossi is really anxious to have some good math team members, and y'all are the prime candidates for the prime, whatever they call it. What's the name of the team? Prime examples, yes. Okay. because y'all have had the most calculus of anyone on campus right now, just about, okay? So please consider doing mathing, okay? Okay, what's the antiderivative of u to the 1/2?
2/3 u to the 3/2.
Okay, u to the 3/2 times 2/3. Only I said half and wrote 3. Okay. Something's a little wrong in the brain, isn't it? Okay, 3/2. Okay. Not minus. What will that one be?
2u to the 1/2.
Okay, say that again. U to the,
1/2.
isn't it minus 1/2?
Oh, yeah, I guess it would be.
Yeah. And what else?
So it'd be times the -2.
-2. All right, so I just changed that minus to plus and put a 2 there. And now and one more thing we got to add. Plus c, because this is indefinite. Okay. Now what do we do? Oh, and by the way, this is so bizarre. I can't believe that. And y'all didn't catch me on it either. Up there I wrote to the 3/3, and then I wrote that to the 2/2. It's supposed to be 2/3 and the 3/2. Oh boy. Okay. Sorry about that. Okay. Now what do we do?
Plug in.
Plug back in what u is and u are, and that is secant x. So that would be 2/3 secant to the 3/2 power of x plus 2 times secant to the minus 1/2 power of x plus c. Now, if you don't like writing it that way, which you may not, I don't know, you could maybe write it this way: 2/3 secant to the 3/2 x. If you move that downstairs, 1 over secant is cosine. So you could write that as plus 2 times cosine to the minus 1, cosine to the 1/2 x. Okay, plus c. Now, I don't know if the book does that or not. Let's just see. I believe they leave it the way I had it. Okay, 2/3 secant to the 3/2 plus 2 secant to the minus 1/2 plus c. Whereas you could have written that as cosine to the positive 1/2, but they chose not to. And that's just another perfectly good example of why I don't like WebAssign, okay? Because both of those are perfectly good answers, and I could come up with another couple of ways you could do it, and they're only going to recognize one answer is correct, okay? But we got it whichever way, without all that in there, okay? Now, that's how we did it. Let's see if they do it any differently. All right, to erase? Okay. Well, first thing to do, because you expect to use the power rule with u equals secant x, boy, they jumped way ahead to see that, and save a factor of secant x tangent x, because that is the derivative of secant x. So you have to pull out a tangent x from tangent cubed. That'll leave you a tangent squared, and they should have already changed it, and they did ultimately here, okay? So that's how they rewrote it, and then they're going to pull out the secant x tangent x dx, and that leaves the secant to the minus 3/2, secant x to the minus 3/2 now. All right, I don't see why they put the 2 here, but put the minus 3/2 there. I mean, why don't you put the minus 3/2 here, or put the 2 out there, but be consistent, you know. They mean the same thing, but it just looks weird to mix them up like that, okay? Now they went and mixed them up, okay? No, they didn't. I don't know what they did. They changed the tangent squared to secant squared plus minus 1, just like Clark was going to have me to do, okay? Now you multiply those through, and you have secant x to the minus 1/2 to the positive 1/2 minus secant x to the minus 3/2. We did it the same way, only we put the powers by the function, okay, times secant x tangent x dx, which is, that is the derivative of secant x, and they skipped doing the u part and just went and dealt with the secant x, okay? And it's correct. We did it. We got the same thing, and that's exactly the answer we got. Any questions on that? I kind of like going on and doing the substitution, but they're just mentally doing everything in terms of secant x, and it's fine. Got it? Any questions? Okay. Now, that was example, goodness gracious, where was that? That was example 4. They skipped 5, they skipped 6, and they skipped 7, okay? So let's go back and us do 5, 6, and 7. Okay. Example 5. Find this. The integral of secant to the 4th x. See, they write, secant to the 4th of 3x. Yuck. Tangent cubed of 3x. Okay. Dx. All right. What do we do here? What do you note first? Yeah, look at the rules. Guidelines. Say again? Power of which? Secant or tangent? Second? Tangent. Okay. Now that's an odd power. Okay? And that would then suggest that you do what? Okay, you can pull out the secant x, tangent x, because that's going to be derivative of the tangent of secant, and that'll leave you a tangent squared, which you can put in terms of secant, and then you have the rest of your secants here. Perfectly fine. Okay? Or you could have done it the other way, pulled out a secant squared, put it down there, and then change that secant squared to a tangent, and you can do it that way. So you have 2 ways to go with this. You like the way you said? Okay, we'll do it. But this one, you have a choice. You have both an even secant and an odd tangent. You get to choose, okay? And you chose to deal with the odd tangent, okay? So what we're going to do is pull out a secant 3x and a tangent 3x and put it with the dx. So that would leave us with the integral of what? You tell me. We're pulling out a secant x, tangent x, and putting that with our dx. So what have you got left? Oh, whoa. 3x. I forgot to put my 3's in there. Say again?
Secant to the 3rd
cubed 3x.
And
tangent to the squared 3x times that. Okay. You don't have to put parentheses. It may help you see it better. Okay? Now, what do you do with that? This is derivative of secant. This is a secant. Yeah. Say again?
We want to change the tangent squared to secant minus.
Exactly. So, and what will that be? Tangent squared is?
Secant minus 1.
Secant squared minus 1. Okay. That's what this is. Okay. So, that's what we write down here. Secant, I can't read my writing, cubed, yeah, 3x times secant squared 3x minus 1 times secant x, secant 3x, I keep forgetting about that in there, tangent 3x dx. Okay. All right. What next? Okay. That will be the integral of
secant to the
fifth 3x
minus secant
cubed 3x times secant 3x tangent 3x dx. Oh, whatever. Don't actually have to have parentheses on that last one, but I did. Okay. Yeah.
Now we're ready
Oh!
to substitute.
I'm hurting. A second.
Now we're ready to substitute.
Okay, so let's do it. Let u equal secant what? 3x. Okay. Let u equal secant 3x. Then
let
du equal
secant 3x tangent 3x.
Secant 3x tangent 3x. You said dx? One other little thing we're missing. Three. Okay? Because when you take the derivative of this, you take the derivative of this part, which you did correctly, then you chain rule it and take the derivative of that, which gives you a 3. Okay. We don't have a 3 there. So how do we rectify that problem? Yes. Do your du over 3, divide both sides by 3, and that will wipe out the 3's there. Now you have du over 3. All right. So I'm going to take that over 3 and put it outside, so that's going to be 1/3 the integral of, and what would the first one be? U to the fifth minus u to the cubed times du. It would have been du over 3, but we pulled the 1/3 out, 1/3 out. Okay? And I think even I could do this one. What would that be? Okay. Ah, Catherine's here. Okay, I wrote down the 1/3 before she walked in. What's the rest of it? Over
6.
Yep. Minus. Eh.
Oh, I mean u to the 4th.
Over.
Over 4.
Got it. And
plus
C. All right, cleaning that up just a little bit and plugging in back what u is or u are. That's secant 3x, by the way. Then this would be, I'm going right up here, I don't have room down there. That would be secant, let me just put the fraction for 1/18 secant to the 6th 3x minus 1/12 secant to the 4th 3x. Goodness. plus c. Okay, I think I got that right. Oh no! Whoa. Secant to the fourth 3x. Remember the 3x, forgot my exponent. Okay, believe that's right. All right, let's see how they did in the book. Oh my goodness. Did we get it all wrong? It looks like it, doesn't it? Unless you were to go in and do a Pythagorean identity there, I bet you'd get the same answer. Okay? You really want to do that now? Okay. Now.
Would it be too much trouble to go back and do it the other way too? So
I was going to say that's how they got it. They didn't come up with a d secant, they came up with a d tangent. They pulled out the secant squared being the derivative of tangent, and that then enabled them to have everything in terms of tangents. So whichever way you think would be preferable, what you would do if you're trying to use Pythagorean identity to do, you write this as secant squared cubed, and then you, and that's not that hard to do. I'm sorry. Secant squared cubed, but secant squared is 1 minus tangent squared cubed, so it is a cubing that you have to do there. And then that was to the fourth, which is even worse, but it will work. And the question is, do you need to see that work, or you want to go do it the other way?
I'd be okay with just doing it the other way.
Yeah, it's fine to do it the other way. And so you want me to just erase all this and do it the other way?
Yes, sir.
I think I'm going to have to, if we're going to do, yes.
What's wrong with this one?
What's that?
What's wrong with this one?
That is a perfectly correct answer. But I just wanted you to reconcile mentally, or however you want to do it physically, that is the same answer they have in the book. Now this is a even better example of how WebAssign would say wrong, and you struggle and say, what did I do wrong? You did nothing wrong. You did it perfectly correctly. It's just another way to express the answer. The question is, do we want to reconcile that? It's sort of up to you. You want to just do it the other way? Okay. Just so you'll see both ways, this is fine. This time, oh, I probably erased too much. Where was it? Down here. Integral of secant to the fourth 3x times tangent to the cubed 3x, right? Dx. Okay. This time we're going to pull a secant squared out because that is the derivative of tangent. Okay. So that will then leave us with a secant squared x, tangent squared, tangent cubed x, 3x, times a secant squared 3x dx. Okay? And again, you're doing that part, and that is the derivative of the tangent. Close anyway, but within a constant. Okay. So, sorry. Since this is the derivative of tangent, we want this in terms of tangent. And what is secant squared in terms of tangent squared?
Tangent minus 1.
1. Yes, okay. Okay. 1 minus tangent squared x, 3x, goodness gracious, times tangent cubed 3x times secant squared 3x dx. Okay, so multiply these two together, and what do you get? What do you get? Tangent cubed 3x minus tangent to the fifth. I can't write 3x. That's supposed to be a superscript there. Goodness gracious. I can't get the pen to work. Okay. I'm clogging up for some reason. That was fifth. Yeah. 3x. And this will be secant squared 3x. Okay. And now what do we do? Let u equal tangent 3x. Then u is equal to, second, secant squared 3x dx times, you don't like change, do you? Ah, yes, times 3. Okay. And then to get rid of the 3, we'll divide that out. Okay. And now our integral in terms of u will be the integral of anybody?
U to the third.
Of what?
U to the third.
U cubed minus
U to the fifth.
u to the fifth.
U to the 1/3.
Oh, yeah, we got a 1/3 out front from this, okay, and that leaves you du. Sorry about that. My screen collapsed on me while I was trying to write, and that's what downhill. All right, and that's a pretty easy integration there. And what would that be? U to the fourth over 4 minus u to the 6th over 6 plus c, and then that would be a 1/12, and just plugging in what it is, tangent fourth 3x minus, I said 12th and I wrote 2, I don't know what's going on here, minus 1/18 tangent to the 6th 3x plus c. And that, I think, is exactly what they got in the book. Now, y'all are just going to take the word for it. Those are the same answers. Okay. It is messy to try to reconcile those two, but it is doable. I'll just leave it like that. If y'all don't care to do it, it's fine. You don't need to. It would take a lot of class time to do it. Okay. Any questions on example 5? Want to move on to 6? You don't say yes, but we're going to. Okay. This one, a couple of issues here. This is example 6. The integral is now a definite integral from 0 to pi fourths. Okay? And you multiply it by the sine squared, no, I can't read, sine fourth x dx. No, tangent fourth x dx. Goodness gracious. Okay. Again. has to go get something. I find it hard to talk. Okay. Now, what do we do here? Second, that's a 0 on the bottom. Sorry, my zeros, I slashed them. And it was a pretty ugly slash. Slash and burn. Okay.
Pull out a tangent squared x.
And why?
Because we need something to integrate.
What's that?
We need something to integrate. It needs to be separated.
Okay. Yes, but you see, tangent squared isn't the derivative of anything. Secant squared is the derivative of tangent. And secant tangent is the derivative of secant. So we're kind of stuck. Okay? Okay, that's certainly something I would consider. Man, I just feel so rotten. I don't know what's happened. I'm clogging up in the head and I can't breathe. So let's do what you suggested there, and let's do the integral from 0 to pi fourths, and write that as sine fourth x over cosine fourth x dx. Okay, now does that help us or make it worse? What do we do with this? Say that again.
You change that to secant. 1 over cosine.
1 over cosine to what?
Secant.
Secant, okay. That's certainly something you can do. And what does that do for you then? That would be a sine fourth x times a secant fourth x. Is that where you were heading? The trouble is there's nothing that relates sines and secants. Okay? So that would be a little problematic. Now, where I would, and this may not get us anywhere either, but where I would tend to want to go is to say, well, let's do this being my u, the cosine x. du would then be minus sine x. Well, that leaves us with a sine cubed x that we don't know what to do with. So I'm not sure that would help us any either. Okay? These are all things to knock around, see if anything sort of pops out at you. Two of those signs you could change to, 1 minus cosine, sine squared would be 1 minus cosine squared, but you still have another sign that you can't do anything with, it seems like. Okay? So let's see if what they suggest for us here. Yeah. Clever little idea. Okay? Since your tangents need secants, we can do this as tangent squared x times tangent squared x dx. Okay, that's pretty obvious, right? Do that as integral from 0 to pi fourths. Okay? Now let's leave one of those tangents and make the other one secants. So what would that be? Leave the first one tangent squared x. The second one becomes secant squared x, what do you say? Minus 1 dx. Okay. Now, has that helped us any? Well, that would be the integral from 0 to pi fourths of tangent squared x secant squared x dx minus the integral from 0 to pi fourths of tangent squared x dx. Okay. Now, that is the derivative of tangent, right? So this first one's going to be pretty good to do, right? So let's do it while we can, before we forget it, okay? And so that will be, you want to do a substitution or not? Yay or nay?
Yes.
What will you do? That u equal what?
The u equal tangent.
Tangent x. Perfect. Then
du
equal
would be has to be tangent squared for it to be secant squared minus 1, right?
okay. Yeah, don't do that. Okay, we were that close. This is the derivative of tangent, right? So derivative of, if u is tangent x, du is secant squared x dx. So now we have u squared du. We can do that, right? Okay. So this will be, now, we got another thing that we have to deal with because this is a definite integral as opposed to indefinite. You have two choices. You can either proceed ignoring this and get it in terms of things and then go back and plug these in. Or, now what you're going to use, we can actually change our limit to the limits of u. Right? Now, which way you want to go?
Let's go ahead and do it now.
Second?
Let's go ahead and do it now.
Change the limits? Yeah, I like that too. If u is tangent x, when x is 0, what is u then? What's tangent of 0?
Is that defined? No, it's 0 over 1.
It's 0, yeah. 0, okay? And what's the tangent of pi fourths? 1. Ha! This one is going to be pretty okay, isn't it? So this will be, and u is tangent, so that's tangent squared is u squared, and du is secant squared x dx, so that's du. Whoa, I think I can do that one in a minute. Let's deal with the next one, though. Ugh. What are we going to do with that? So we kind of just put this off till the very last, but we still got to deal with the tangent squared. Now, how do we do that? Your idea earlier. I don't, oh, that may not work. I was thinking change it to sines and cosines. You still have the sine squared in the numerator, and all we want is the sine. Okay? But somebody, I think it was maybe Clark, had the idea, what do we do with tangent squared?
Change it to secant minus 1.
Second. Yeah, secant squared x minus 1 dx. And what's the antiderivative of secant squared? Tangent, yes. So let's do this first. What will this integral be? Oh, and I put pi halves. Where did that come from? You tell me. That's a pi fourths. Okay. Never mind. What's the antiderivative of u squared? Let's do that one first.
U to the third.
Yes.
Over 3.
Okay, and that's evaluated from 0 to 1. Right? Okay. Minus, and what's this one? Antiderivative of secant squared. Oh, you just said it. Tangent x, and that's evaluated from 0 to pi fourths. Okay? And what's the, and here we have a minus and another minus, so that's going to be a plus. And then we have the antiderivative of 1 dx. Well, so we've done this one, let's do that one now. Antiderivative of minus 1 dx. X, all right. That would be x, evaluated from 0 to pi fourths. Okay. Now, u is evaluated from, so that would be u evaluated from 0 to 1. That would be, or u cubed over 3. That would be 1. Okay, right? 1/3. Yeah, 1/3. Yeah. 1/3 minus, and what's the tangent of pi fourths? 1 minus 0, 0. And then we have a plus pi fourths minus 0. So that will be, I'm going to rewrite it as pi fourths minus 2/3. Strange answer, but should be true. Let's see what they got. 1/3 minus 1 plus pi fourths, which they wrote as 0.119. Why didn't they write it as pi fourths minus 2/3? Okay, pi fourths. Remember, pi is about 3, so that's almost 3/4 minus 1/4. I mean 2/3.
So that tangent there would not be tangent squared if we did secant.
No.
Squared x minus 1.
The antiderivative of secant squared is tangent. Derivative of tangent is secant squared, right? Okay. Now, I disagree with their answer. Okay? No, that's right. As I was saying, this is about 3/4, and this is about 2/3. So 3/4 is close to 0.7, is 7. Okay. This is close to 3/4, so that would be close to 0.75 minus 0.67. So 0.119, that sounds about right. Okay. Ballpark. Okay. You can do it with the calculator, come out exactly, but that does sound right. Okay. Does that make sense? Okay. Now, example 7. Okay, find this integral. Secant x over tangent squared x dx. Secant x over tangent squared x dx. All right. Now this one, you might think Pythagorean theorem here. That would give you a secant squared minus 1 over that. No, that's not going to help you any. Okay? Derivative of tangent secant, derivative of tangent secant squared. You don't have that. That's not going to do. So we're really in a bind, And that's why we're so glad Vince came in to help us out, okay? Now, what are we going to do? Your idea from before. Sines and cosines. Let's see if that works. Because nothing else seems like it's going to work here. Okay, so let's do that. That would be the integral, and this is an indefinite integral, right? Yes. Okay. Now, what is secant x? 1 over cosine x. Now, what is tangent? Sine over cosine, but tangent's in the denominator, so the sines are going to be here. That'll be sine squared x over cosine squared x. Right? Y'all buy that? That was a shell game. I did a lot of things at once. dx. Okay. Now, I hope something's pretty obvious about what you can do. Yes. Wipe out one of the cosines. Okay. So now your integral looks like this. The integral of cosine x over sine squared x dx. Can we think of anything to do there? First and foremost, you might want to rewrite it. What would that be then? Remember, yeah. I don't like denominators or radicals. I want to get it in exponential forms. So what would that be?
Cosine x.
Cosine x.
Sine to the
Sine to the
negative 2x.
negative 2 x dx. All right, now does that stimulate a thought? Not really, huh? All right, really? Okay, what?
I mean, now we can use substitution.
Yes! And what would you substitute?
Would you want to substitute let u be sines?
Yes, 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 yes. Sine x. Okay, then du is equal to cosine x dx. Hey, there's our du right there. So what do we have here? The integral of u to the negative 2 du. Ha! I think we can do that one. What would that be?
U to the negative 1
Over,
negative 1.
which it could be the same as times plus 1, times negative 1, right? Divided by negative 1, multiplied by negative 1, same result. And one other little piece, plus c, and then what do we do? Plug it in, and what does that give us?
Negative sine negative 1x.
1 over sine x plus c. And what in the world is 1 over sine x? Cosecant. Okay, negative cosecant, if I could write, x plus c. Now you don't, I don't know where that came from. I say c, and we're not talking d's anywhere, and a d shows up. Okay? All right. Okay. Now, I'm sure the book probably doesn't do that as an answer. Oh, they do. Look at that. Surprise, surprise. But that's a perfectly good answer up above it. Okay? And there's no reason to make that cosecant. It's just a little easier to write. Or you could write it as minus sine to the minus 1x like they did. But you know, if you left it like that, well, the sign will say wrong when it's right, you know. So that's why. Never mind. Enough of that. Any questions on those? So you got a variety of ways to go. If it fits the rules, use the rules, okay? If it doesn't fit the rule, then you got a lot of trial and error, guessing, let's see if this works, insight, whatever it takes to see if you can make it work. If you can't use Pythagorean theorem and derivatives and stuff, and you just completely run out, try sines and cosines and see if that'll help. Sometimes it will. Sometimes you have to go back and think of something else. But that's what we got. Now, ready to move on? Okay. Integrals involving sine, cosine products. Okay? I thought that's what we were doing. Okay? Except that what they're saying here is we're using multiple sine of multiple angles, cosine of multiple angles. So integrals involving the products of sines and cosines of two angles, different angles meaning, occur in many applications. In such cases, you can use the following product to sum formulas. Now, I remember doing these in trig and saying, yuck, whenever you ever going to need those. Yeah, they're interesting, they're fun, yeah. Well, here we are needing them, okay? And this is just reproducing them for you. I could show you how they got these, but it's better just look it up and say, this is what they are. But, well, let me go and remind you. Remember cosine of a difference? That is cosine mx minus nx. That would be cosine mx, cosine nx, plus sine mx, sine nx, minus, and you do the same thing here, this would be a cosine mx, cosine nx, minus, you do another minus there. Yeah, so you keep on, and the cosines cancel out, and the sines add together, and that's why you divide by 2. So that's how you get this. This one comes from the sum and the difference of sines. Okay? Sines of sums and differences. And this one comes from the cosines again, but you put the plus in here, so you are left with that. So this is where they came from. And when you need them, use them. Frankly, I would look them up rather than memorize for sure, or I could go back and reproduce it from scratch. Now, there is something I find kind of interesting here, is their use of parentheses and brackets. And I'm not sure a computer program, this would drive it crazy if you tried to do this. If I were doing this, I would probably put a brace here and a brace there. So you have parentheses here, brackets here, and brace on the outside. Parentheses here, bracket here, and brace on the outside. Just to keep them separate. Because what I'm guessing, if this was a computer, it was going to, so this first parentheses, try to do this and then try to close out that parentheses there. I don't know. Maybe computers are better than they used to be, but I think it would try sort of drive that computer nuts trying to figure out which pair the parentheses goes with. So I don't know. I haven't done any programming lately. Maybe computers are smarter than they used to be. Okay. So here's one. Example 8. Using a product to sum formula. Sine of 5x cosine 4x. Well, you can flip the page over. No, it's on the same page, isn't it? Yeah. Just look above to the sine cosine. That's the middle one. And what would that be? Well, you have the 1/2. So let's pull the 1/2 on the outside of the integral. Okay? And then we'll do the integral of, and that's the sine of 5x plus, no, I'm sorry, 5x minus 4x. I'm sorry, I almost said it wrong. So that would be x, okay, plus, that's where the plus is going to be, the sine of, and this time we add the two together, that would be 9x dx. Okay? Got it? That's just looking above and using the formula. Be 1/2. What's the antiderivative of sine x? Negative cosine x. And what's the antiderivative of sine 9x?
Negative cosine 9x.
Got it. Negative cosine 9x. But then you got to basically undo this chain rule. If you're taking derivatives, you multiply. Integrating, you divide. Okay? And then you do your plus c. Okay? Now that would be an okay form to leave it, I think. Okay? Or you could do, I'm so sorry, minus cosine x over 2 minus cosine 9x over 18 plus c. To me, that's just a little bit neater, and that's how they did it too. Minus cosine x over 2 minus cosine 9x over 18 plus c. Perfect.
So on that first negative cosine x there, if that had been negative cosine 2x, it would have been over 2.
It would have been over 2 here. You're absolutely right. Yeah. Because you're undoing the chain rule, you might think. And here's what you do. You think, what happens if I take the derivative of this? That would be a minus 1/2 times the derivative of cosine would be minus sine. So that makes it plus 1/2 sine. And that's exactly what you got, 1/2 sine x. When you take the derivative here, it would be 1 over 18 times the derivative of this, which would be sine of 9x, chain rule times 9, the 9 over 18 makes it 1/2. And that would be 9x. So always undoing chain rule thing, it usually is helpful to go back and take a derivative and make sure you did it right. Okay, and we did. Okay, any questions? Excuse me, on that? Man. Okay, it says to learn more about the integrals involving sine cosine products with different angles, see the article Integral of Products of Sine and Cosine with Different Arguments by Cherie Nicole in the College Mathematics Journal. And they have a link you can go to. That could be a paper topic if you wanted it to. That's something outside the book. You'd have to go get it. And that might be useful. All right. Oh, wait. I forgot. They have this one shown. So let's erase this and see what we got. Considering the second product of sum formula, that was the middle one, that would be 1/2 the integral of sine x plus sine 9x dx, which would be 1/2 of antiderivative of sine is minus cosine, just like you said. Antiderivative of sine 9x would be minus cosine 9x over 9, undoing the chain rule, plus c, and that would be minus cosine x over 2 minus sine 9x over c. Okay. All right. Let's move. Before we move to 8.4, homework exercises 8.3. Any of the odds, 3 through 13, they're all at Calc Chat. 7's at Calc View. Any of the odds, 15 to 19, they're all at Calc Chat. Any of the odds, 21 to 33, they're all at Calc Chat. 27's at Calc View. Either 35 or 37, they're both at Calc Chat. Do 39, it's at Calc Chat. Oh, man. It's hard to see. Do 41. It's a calc chat. Then do any of the odds 43 to 47. They're all a calc chat. 43 is a calc view. Do any of the odds 49 to 57. They're all a calc chat. Goodness gracious, it's hard to swallow. Do any of the do any of the odds 59 to 65. They're all at calc chat. 63 at calc view. If you're interested in exploring some of the concepts, and you might find these interesting, you could try either 67 or 69. Both of those should be at calc chat. Okay. Then do number 71. That's a calc chat. Okay. Do 73 if you can. That's a calc chat. 75 is a calc chat. 77 is a calc chat. Do any of the odds, or either 79 or 81, they're at calc chat. 83 or 85, they're at calc chat. 87 should be a calc chat. 48 series, which is number 89, should also be a calc chat. Okay. All right, there's a lot there about the Wallace product, but there's no specific exercises. So you can certainly look at that and go for it. All right. I'm going to have, I hate to do this, but I have to call a timeout here and go and get something to clear my head, because I'm having a harder time breathing. So I'm going to pause this for now. Does anyone need this up? Well, there's nothing to copy off of it. So let me just pause this. A very short lunch on every day, really. But, so I sort of gobbled it down in a hurry. I had a phone call right at the end, and I didn't get to drink very much. I think that's why now I'm so dried out, as I've been doing all this talking with very little moisture. Sorry about that. Okay. Let's go from current slide. Let's start. Hope I'll get cleared out, because I did drink quite a bit while I went down to my office. So here we're going to do integration techniques and improper integrals. Now I'm going to focus on the integration techniques and kind of leave the improper integrals for later. I mean, well, just not do them, because we need to move on some. So let's start with trigonometric substitutions. Okay, again, that was the chapter title. These are the techniques. Oops. We'll use a trigonometric substitution to find an integral, and we'll use integrals to model and solve some real-life applications. You see that almost every one. Now, the last section was integrations of trigonometric functions. This one is trigonometric substitutions, okay? Not trigonometric integration of trigonometric functions. So it sounds almost similar, but it's a different approach. And here's what we're going to be looking at. Anytime you have a radical such as this, the square root of a squared minus u squared, the square root of a squared plus u squared, or square root of u squared minus a squared. These lend themselves to, and wherever you find these may be in numerators and denominators or mixed up in, whatever. These will lend themselves to trigonometric substitution. Because if you try to integrate this, you're going to have a hard time. There's no du to be found here, okay? So you're in trouble, okay, if you don't use the trig substitution. Now, here's the thing that I use to remind myself of why you do this. I think of sines and cosines. Let's go with sine. Well, either one. A sine, and these are all squares. So I think Pythagorean identities. They're squared, right? Think of a as the 1. If it's not a 1, you can make it a 1. I mean, you can fiddle with it and get it to 1. and u being this. Well, 1 minus sine squared is cosine squared, or 1 minus cosine squared is sine squared. So that can undo this for us, you know, and we'll be in great shape. Ha! 10 o'clock scholar. Okay, Charles is here. Okay. All right, so we're just missing Jordan. Okay? Guess he ever came in. This one, think tangent. Because 1 squared plus tangent squared is secant squared. And then you can take the square root of secant squared and get secant. And you can go with that. And then this one, secant squared minus 1 is tangent squared. Okay, what if they're not 1s? You can fiddle with it and make them 1s. Okay? So the objective with the trigonometric substitution is to eliminate the radical by finding a perfect square you can pick under there. And that can be a cosine or a sine. It could be a secant, or it could be a tangent. It's what it's going to go under there. But you use the sine or cosine substitution here, a tangent substitution here, and a secant substitution here. Okay? You do this by those Pythagorean identities. All right? So here's an example. Now here's an issue. I meant to say this back when we were doing an earlier problem. Remember that one that had tangents and secants in it, but it went 0 to pi fourths. Remember that one? It had to do that. Remember at one time I had written pi fourths, but written pi squared, pi halves. Couldn't do that. Why not? Tangent and secant at pi halves is undefined. So you couldn't have possibly done that. That's why you had to keep it somewhere in the range that you don't cross the vertical asymptote. Okay. So, the example, if you have a greater than 0, you don't have all negative a's, then you're going to let u equal a sine theta and keep theta between minus pi halves and pi halves. Okay? Now, why is that? Why would theta need to be between there? Well, if you think about it, sine is monotonic in between there. Okay? So that's probably going to work pretty well. And it can equal either one of those endpoints. Okay? So if that's going to be your substitution, then you do that. U is equal to that. Well, then u squared would be a squared sine squared theta. So this would wind up being the square root of a squared minus a squared sine squared theta. Factor out an a squared, and you have the square root of a squared times 1 minus sine squared theta. That would be a squared times cosine squared theta. Well, the square root of a squared is a, the square root of cosine squared is theta, cosine, and guess what? You can integrate that because we know how to integrate sine and cosine. We don't know how to integrate a radical with a square in it because you need a 2u somewhere out there and you don't have it. Okay. So that's why this substitution works for you. Note that the cosine theta is always greater than or equal to 0, especially if you stay between minus pi halves and pi halves, right? The cosine is always positive there, or equal to 0 at the end. Okay? But that's why you chose this. If you had a cosine going from here to there, this part positive, that part negative, you get 0 as your answer. So that's not very helpful. So you have to watch your endpoints. Okay. So that was the lead-in. Here's the other thing when you do these substitutions. Okay? Draw you little triangles. Okay? You will find these helpful in the long run. Okay? So if you're having an integral involving the square root of a squared minus u squared, and you say let u equal a sine theta, that's what we did. Okay? So you want this to become an a squared here, and you want to be able to subtract out. Well, then let's write down what you've got there. If u is equal to a sine theta, rewrite this as sine theta is equal to u over a, right? What is sine theta? Just draw your triangle. It doesn't have to be any special triangle. Make it a right triangle, of course. Some angle theta here. Sine is u opposite over hypotenuse, u over a. So take that your u, make that your a. And guess what then? The side over here is the square root of a squared minus u squared from the Pythagorean theorem. And there is exactly what you've got there. So here you got this little triangle will help you out of a lot of mess, a whole lot of mess. And then, as we've already said, when you plug this in here, you get this thing becomes a cosine theta, as long as theta is between minus pi halves and pi halves, which means it goes from down here to up there. Okay, don't want it going anywhere else. Cosine would be negative in the other two quadrants, so positive in the fourth and the first quadrant. And then if you've got this one, a squared plus u squared, use a tangent, okay? And if you let u equal a tangent theta, rewrite this as tangent theta is equal to u over a, right, again. But the tangent of theta is opposite over adjacent. And there you have it, and this thing here is your hypotenuse, the square root of a squared plus u squared, right? So that works out perfectly. And when you're using this one, your substitution will be a u is equal to a secant theta, so everything comes out there. Well, write this as secant theta is equal to u over a. Secant theta is hypotenuse over adjacent, u over a. And this becomes your square root of u squared minus a squared. And that's exactly what you had here. Now, this one again is good from minus pi halves to pi halves. Notice a little bit of a difference between these two. This includes the equal sign because that's perfectly okay there. This one can't include the equal sign because both the tangent and the secant are undefined at the half pi's because that's where you're dividing by 0. Can't have them there. So this includes the equals, this one does not. This one down here, on the other hand, what you have to do with that is it's a mess. And usually it's not anything you really have to worry about, but you might at some point. Let's see. I can't think if there's an easy way to explain this. I usually don't even mess with something like that because that is almost not physically reasonable, okay? And the reason I say that, especially if you use this triangle, u can't be less than minus a. Yeah, we think of u as always, the hypotenuse is always positive. How can it be less than a negative number, okay, if that's a minus a? And so it just is a little bit of a mess. And part of that comes from where you are. This part is good anytime u is greater than a. Of course that would be, because if u is greater than a, then this is a positive number here, right? And then your angle is going to be between 0 and pi halves. Now, if u is less than a minus a, it still doesn't make any sense to me. Because u squared is going to be then a smaller number than a squared is. Okay? You're going to have minus. So, frankly, I don't think I can't remember ever running into needing this. So, we'll just use it for this. Most of the time. Now, if we run into one, I'll say, okay, there's the exception. But I can't think of where that would actually happen for us. Okay, so let's do one here. Oh man, they start with, are we almost out of time?
Yes, sir. That would be working.
Oh yeah, what time is it? Oh, I brought my watch. Okay, what time do we end?
2:10.
2:10. We're there, aren't we? All right, we'll start next time. Sorry I had to take a break. I should have just hung through it, okay? We'll start next time with example 1. Top of page 542. And we didn't get enough done in here to do any homework exercises, so we'll just go from that point. All right. Any questions? Okay. Good. We will see you Monday. Oh, wait.
Wednesday.
Oh, bad news, or good news, bad news situation. Okay? The good news is that Monday's a holiday, Martin Luther King Day. The bad news is we won't have class. So get over it. Okay.
Just look at those video things.
What's that?
The video thing.
Well, probably just skip it. We'll pick up here on Wednesday. I think we're all right.
Yeah.
Okay. Good deal.
Well, you guys have a good one.
You too. Okay.
No Monday class.
That's true. Sorry about that.
It's fine.
See you tomorrow.
Okay. Yeah. I'll see you tomorrow.
And then get some more hours back at work.
Okay. Let me end this.
Make these middle of the day classes is making my work schedule tough.